Hi there. I think so. We're just having some trouble with this. Thank you very much. Nice. Oh, nice. You have something else. The guys from checking out. Here it comes. You then have a scooter because you quit. I never. Fantastic. Are you going to do the chair slides? Nice. Yeah, otherwise you'll be, well, not I have to do one of the presentations. You have to do both of these. Let me get the sheets right.
Send you.
Yeah, I know. Thank you very much. Nice. Almost. Alexei almost wasn't here. Came in like a minute ago.
Oh, yeah, I seen one with yesterday, so I knew it was here.
Yeah. No, but in terms of coming to the room. Wait, who's that? Thanks, Alex. We also have a presentation. Well, we have Micho as well. Yeah, I'm not quite sure how any of that works. We'll figure it out as we go.
Red button.
That's it.
So they come, you push one, you admit them, you push second time to eject them.
And then just appear on the loudspeakers.
Yes, it should appear on the thing. And if it depends whether they have video or not.
Yeah.
If it sometimes it doesn't, you try it twice and you ask them to rejoin. But oh yes, just got your message. Right. Sorry.
Do you want to use this?
Oh. Are these? Good afternoon, is it? Good afternoon. This is Cfrg session at IETF 99. So I hope you're in the right room. We have note taker, we have person Rich relaying from Jabber to the mic. We have blue sheets going around. So let's get going. We have quite a busy agenda this time. There were lots and lots of requests in the very last moment, so that sounds all very exciting. Okay. How do I? Down. Okay. Actually, agenda bashing. Can we? Oh, can you click on this? Is it going to work? Okay. Sorry, just very quickly, we'll do agenda bashing. If there are any changes for people asking to move stuff around. Going once, going twice. Okay, then we'll just get on with things. Okay, thanks. Right, I assume you all seen the note well, and which applies to IETF and equally applies to RTF. Okay, we've done that. You see two chairs in front of the room. So Kenny sitting next to me and me, Alexei. So I hope you all know who we are. Just very quickly about status of various documents. This is since Seoul because we haven't officially met in Chicago. We got two RFCs published, which is good. We have a couple of documents in IRSG review. They're either being actively reviewed or there are some comments, so they need revisions to documents. We have 3 or 4 very active documents in the working group. I think Argon 2 and GCM SIV are nearly ready for our last call. We already had some early reviews for the GCM SIV document. Rekeying document editors are being quite active. Also, there was an official meeting in Chicago, so there were some revisions and presentations going to be later on today. Yes, I think that's the main thing. The other thing the chairs would like to say is we started crypto review panel last September, and we were a bit slow getting up to speed and getting the panel reviewing documents, but we had lots of very good reviews recently. GCM SIV got 3 or 4 reviews. I think even Kenny and I were surprised how much interest there was in this. So I think things are working well. So we're looking forward to using crypto panel more in the future. Okay. And at this point, let's start with presentations.
Okay, so first up we have Stanislav, who's going to update us on rekeying. Stanislav, I think we allocated 10 minutes in the agenda for your talk. And please try to stay, this is for all speakers, please try to stay inside the pink box. That's where the video will find you. And I'll be doing, just ask for next slide each time. Okay, thank you.
Okay. Good afternoon, dear colleagues. Stanislav Smishlev, CryptoPro. And my talk is dedicated to the current status of rekeying document for symmetric keys. So the current version of the draft is 0.5. The main authors are on the slide, And let me say some few words about the motivation. So,
I have the control.
okay,
You have to ask me the next thing.
okay, thank you. So when we have encryption in process and we need some limits to be on our mind to be taken into account. First of all, these are just general combinatorial properties, estimations for used ciphers if they have some potential vulnerabilities, and the most important of all, side channel cryptanalysis methods of block ciphers. So, for example, there was a good paper recently about Tempest attacks on AES, with attack taking only 50 seconds to get an AES key from OpenSSL implementation. So, taking into account these problems, we have to limit the key usage, the key lifetime, and when our limits are reached, we have to change keys. So, of course, we can just do a new handshake, do a new key establishment, but it can be quite expensive. So, in a lot of stations, we prefer to update the keys, so to do the rekeying. A great example here is a rekeying procedure in TLS 1.3 as a key update procedure. And I think that this is a good example how, when, and in which stations rekeying must be done. Please, next slide. So the main objective for the document is to prepare a document with a menu of choices for the developers of protocols that at first contain a lot of secure and efficient procedures that solve the rekeying task in most relevant cases. Of course, this document shouldn't be redundant, and this document should contain general recommendations and choice principles for the rekeying mechanisms, one or another, and with some specific parameters. We consider both external and internal rekeying methods, parallel and serial, hash-based or cipher-based, with and without master keys. For the vast majority of them, the security increase is about quadratical. So the key lifetime can be increased approximately quadratically in most relevant models. Please, next slide. The work started after Seoul meeting. There was a proposal from the Cfrg chairs to create such a document. There was a talk on rekeying at Seoul meeting. We had discussion, and then the work started. The 00 draft and 01 draft appeared before the Chicago meeting, and in Chicago we had a 1-hour side meeting on rekeying, where we had some important decisions about the document. Please, next slide. Please, next slide. Thank you. So, first of all, about the considerations of the scope and aims on rekeying. We decided to focus on the following 4 features, the following 4 reasons to use rekeying. First of all, again, it's additional side channel resistance. Secondly, in some cases, in some types of rekeying, helps us to gain PFS security regarding segments of encryption process. Then, if you use ciphers with short block sizes, for example, for lightweight cryptography, rekeying is used just to extend the key lifetime, because just the combinatorial properties limit us with too strict limitations. And then most complex issue here is an additional security against possible attacks on the used ciphers. We added a remark to the draft, and also there is on the slide, that this must not be used as a method to prolong life for broken ciphers. It's just a security margin, a safety margin against possible future attacks. So it's not, it mustn't be used to prolong life for something already vulnerable. Some words about post-quantum issues are added. No post-quantum issues can be solved by rekeying, because if we talk about Grover's algorithms, we can just talk about attack on 2 or 4 blocks are sufficient for us to mount the attack, so rekeying wouldn't help. And some words about reasons that remain for even for ciphers with large block sizes were added about side channel resistance, PFS, and again the safety margin. Please, next slide. About the recommendation guidelines. The most complex question here was about the limit between the external and internal rekeying, and now we base this part of draft on the following concept, that external rekeying is chosen on a protocol level, while an internal rekeying mechanism is chosen linked to block size and block cipher mode operation. So the most important thing here is the mode operation, and when we try to understand which frequency to use with rekeying, it's dependent on a block size. Then we added a text about advantages and disadvantages from those slides, provided sample cases, working examples, and some toy examples for protocols. We rearranged the document so that the recommendation part and the motivation part is before the mechanism itself. And there was a decision not to consider any related questions for SWIP ciphers because all models there are quite different. Please, next slide. And on the mechanisms themselves, there was a number of minor considerations about constants in the internal rekeying for CTR mode. The most important consideration was about the CCM mode. There was a proposal to consider also a CCM mode with rekeying. And I'll return to this question a bit later. Please, next slide. So after the Chicago meeting, we had 4 more versions. The current version is 0.5. We had 2 major revisions after a list of considerations by Russ Hasley, by Shay Goron, and Dmitry Belявsky. And the current version is 0.5. Of course, we'll be happy to have any reviews or considerations for this version. Please, next slide. We hope that the structure, the principles, and the major recommendations in this version are quite close to being ready, but we still have a lot of important questions to be solved. First of all, as I mentioned before, internal rekeying for CCM. Now we have a proposal for mechanisms for internal rekeying for CCM. It's added to the draft, but there's a problem with it that now this is the only mechanism that doesn't have security proof. For all other mechanisms, we either have full security proofs or they can be obtained by some slight modifications of the existing proofs because principles are the same as in the existing proofs. But for CCM, because of authenticity problems, we can't get security proofs using the things we have now. So it must be done from scratch. If so, we need help here, and if someone would like to help, it will be great. And for now, we think that if we aren't able to obtain also security proofs for CCM with rekeying, we need to exclude the mechanism because we don't want something without security proofs, explicit or implicit, to be in the document. Then we are thinking about adding a section about key trees, a key hierarchy in terms of NIST SP 800-108. Of course, we'll need to add test vectors, and also I would ask for considerations and concerns for the current version. First of all, opinions about whether all the concerns from the Chicago meeting have been properly addressed, and any new comments, first of all, about the recommendation and usage cases for protocols. For instance, from the IET field. I think it will be very important to have as much refined formulations about recommendations from the developers of protocols as we can. Next slide. So thank you very much. Questions, considerations?
Thank you very much, Stanislav. So we have 10 minutes allocated for questions and discussion of this draft. So please approach the mic and state your name in the usual way, and then we'll get into your questions and comments.
Hi, Yoav here. Few slides back, I had this distinction between 64-bit ciphers and broken ciphers. So concretely, is triple this broken or just 64-bit?
It's a good philosophical question. I don't think that it's in the scope of the draft, but in my opinion, the document is about the ciphers that don't have even any theoretical problems. So I don't think that 3DS must be in the scope of the new protocols, and I don't think that anything must be strengthened with rekeying if we have some theoretical problems with it. So in my opinion, 3DS must be out of the scope, but it's just only opinion. We don't have to add some such thoughts in the document itself.
Okay, so are there any ciphers in use that are not broken and 32-bit or 64-bit?
If the, my opinion is that if the real security for now, for the known attacks, is the same as a priori security, then it's everything is okay with the cipher. So we have some, for example, 32-bit cipher. Of course, we have some a priori limitations for its usage, of course. But if we don't have any attacks then that can lower the theoretical security, then we can understand that the cipher is still unvulnerable and it can be considered. So in my opinion, we have to distinguish the ciphers with a priori low security or broken ciphers.
Okay.
Daniel Franca Akamai. I've actually been jokingly subtitling this draft as "Make 3DS Great Again." So I mean, actually going out of your way to apply this mechanism so that you can use 3 days seems like a questionable life decision. But nonetheless, I think it is almost a canonical example of what this mechanism can do. It can take a cipher where the best attacks are generic attacks, but the generic bounds are not great, and make them more comfortable.
Yes, I totally agree. So if we have only generic attacks, then it's a good way to prolong the life of a key with this mechanism. Thank you. And thank you for reading it once again, Daniel.
Maybe we could ask for a quick show of hands from the audience, now putting you guys on the spot. Who has read the draft? Oh, that's fantastic. Great. Are there any, yeah, should let you get your hands down first. Are there any volunteers to do a thorough review of the draft on behalf of CFRG, now that it's reaching a fairly mature state? Any, can you put your hand high and then we can take a photograph? Ah, that would be really helpful. Thank you so much. Anybody else? Of course, we can make use of the CFRG review panel, but we don't want to make that the exclusive mechanism by which CFRG drafts get reviewed. We want to continue to involve the wider CFRG membership in that kind of process. Okay, Alexei?
We're also always on the lookout for new, new future panel members. So, that's a great way of demonstrating your capabilities.
Okay. If there's nothing else on this one, then we'll move on. Thank you very much, Stanislav.
Thank you.
Thank you. Should I give them a clicker? Should I give them a clicker? Yeah, I put it.
Okay, so I presented this draft at SAG at the last IETF. We were asked to bring it here. It's substantially updated. So what I'm going to do is I'm going to go over, for people who didn't see my SAG presentation, I'm going to go over what exactly a verifiable function, random function is and why we should standardize them. I'm going to talk about the applications, and since that meeting, I have more information about what the applications of this primitive is. People are using it in ways that I didn't know before. And then talk about what's new in this draft. Okay, so to get an idea of what a verifiable random function is, we all know what a hash function is. It doesn't have a key. You take an input, it gives you an output, and to verify that the hash was done correctly, you just recompute the hash yourself. Okay, so there's a verification mechanism for this hash function. Next slide. A PRF has a symmetric key. The holder of the key can compute the hash, but if you don't hold the key, you cannot verify that the hash was computed correctly, right? So that means that there's no one-to-one relationship between the input and the output with a pseudorandom function. With a VRF, it is a keyed hash function. Next slide. It's a keyed hash function, but this time we have an asymmetric key. So the way to think about this is sort of like the public key version of a keyed hash function. And what happens is in order to compute the hash, you use the secret key. So that means only the hasher can compute the hash, but anyone can verify that the hash was computed correctly. So that gives you, we're going to see that that gives you a one-to-one relationship between inputs and outputs if you know the public key. Okay, so that's what we want from a VRF. Cool. Okay, great. Love it. Okay, so how does this work? So I want to go over the API of how a VRF works. So what happens is the verifier holds the public key, the hasher holds the secret key. He sends his input over to the hasher. The hasher computes a value called the proof. So the way that's computed is by taking the secret key and the input and computing some value called the proof. Okay, so only the hasher can do this. Now the verifier needs to verify that this hash is correct. So it's going to run the verify function using the public key, the input, and the proof. If that comes out valid, then he can get the actual VRF hash output, which just is derived directly from the proof. So you can think of it as just taking the proof and hashing it in some way, and that gives you the VRF hash output. Okay, so the way you verify is with the proof, but the actual hash output is computed using this proof to hash function on the proof itself. Notice that the proof to hash function is not keyed. Okay, so the keying is for the proving function, the public key is for the verify function. Okay, so what are these things useful for? So the way we came to this is through NSEC 5, which is solving the zone enumeration problem in DNSSEC. It's also used for key transparency in the Connix project and all sorts of derivatives of these projects. In both cases, VRF is used to prevent dictionary attacks. Okay, and we're going to see exactly why this works. Since then, I also found that it's being used by cryptocurrency called Algorand. In this use case, it's a little bit different. What they're doing is to do randomized selection that can be verified. And I'm not going to talk about this application in this presentation, but I'm happy to take questions about that. After we started talking about VRFs in various venues, we started to find various implementations, slightly different implementations of the same underlying idea. Okay, so it comes from the Shom-Penderson proofs that are used on elliptic curves. Very, very similar ideas, but a lot of them were flawed. When I say flawed, I mean seriously flawed in the sense that you could break uniqueness, and uniqueness is the key property of VRF. So I'm going to show you in the next slide what uniqueness is, but I believe that a standard would be very helpful because of various different implementations of this, some of which actually had this bug that was fatal for a VRF. Okay, so now let me show you the uniqueness property, which is one of the key properties of a VRF. So what uniqueness says is that there's a one-to-one one-to-one relationship between the input and the hash, as long as you know the public key. Okay, so if you think about SHA-256, if I hash X, I'm always going to get Y. It's not going to come out to a different value every time I do the hashing. A VRF will give you the same property, that every input maps to a unique output given the public key. Okay, and that's why you can use a VRF the same way you might use a hash function. You know that there's a one-to-one relationship between the input and the output. More formally, what this says is even an adversary that knows the secret key cannot find two outputs that map to the same input. Okay, so it can't be two outputs that map to the same input. We know that there's a one-to-one relationship between the input and the output, even if you know the secret key. And that's the same as with SHA-256, right? We have this type of relationship with that. Similarly, we want to have collision resistance, even in the face of an adversary that knows the secret key. In this case, if the public key is fixed, even an adversary that knows the secret key can't find two inputs that go to the same output. So these two properties give us a nice one-to-one relationship that allows us to use hash functions and hash-based data structures. Basically, you can substitute your hash function with a VRF. Okay, but why would you want to use a VRF? It's this last property, which is pseudorandomness. And what it says is, if someone gives me a VRF hash output, I have no idea what input it corresponds to. Okay, so if I just get the hash value, so notice what's happening here. The hasher is computing the proof, then computing the hash by taking proof to hash of the proof. He gives me the VRF hash output. I, as the adversary, have no idea what input this hash corresponds to. I cannot do a dictionary attack where I test all the inputs in my dictionary, hash them, and see if they match this hash value that was given to me. I cannot do this because I don't have the secret key. Okay, so that's why VRF is actually useful in a lot of these use cases, is because it prevents dictionary attacks. Okay, so if this isn't clear, please ask me questions in the question and answer section, but this is the real important thing. So it acts like a hash function that stops dictionary attacks. And this is just the formalization of what I just said. So these two use cases, which are where we started with this, are about preventing dictionary attacks. Just want to briefly show you kind of what the idea is here. Forgetting about VRFs for a second, and I'm sorry, there's public key and secret key on this slide. They shouldn't be there. In the normal case where we have a hash-based data structure, we have the root of the data structure. The querier will send a query to the hasher. He'll give him some sort of information from the data structure. So in this case, I'm drawing like a Merkle tree of getting the Merkle path. Anyway, it doesn't matter. He gets some information. He learns this information about the data structure, and he can verify that his input is in the data structure. But if he does this a bunch of times, he starts to learn a lot about the data structure, right? So the second input, he gets another branch, and you can imagine he keeps doing this, and he can get the whole Merkle tree and so on. Then he can start to do things like dictionary attacks to try to learn what exactly is present or absent from this data structure. Okay, so this is where VRFs come in. If instead of using a regular hash function, we use VRF hashes, then now when I want to get the answer to a query, I have to ask the hasher to answer the query for me. I'll get still the part of the data structure that I'm querying about, but I'll also get this proof that only the hasher can compute. Okay, and then I'll use that proof to verify, first of all, that the hasher answered me correctly. So I'm going to take the proof, the input, and the public key and run the verify function. Then I'm going to get the hash value and check that the hash is in the data structure. So it's just like what you would normally do, except you first need to do the verify function and reject if verify fails. Okay, so this property ensures that the hasher cannot lie to you about the output. And the VRF's pseudorandomness property ensures that because you can't compute hashes on your own, you can't start reversing hashes and trying to enumerate everything in this data structure. And that's what we're using it for in NSEC 5. That's what's being used in Connex, in key transparency, and all these other applications. Okay. So what's new in this draft? There's two VRFs specified in this draft. The more efficient one is the elliptic curve VRF. We've done so when we were designing this, we wanted it to be fast. We wanted proofs to be very short because the proofs are the things that are on the wire. So as you can see here, the thing that's traveling around on the wire all the time is the proof. So we really don't want that to be excessively long. For various applications, this is important. In order to optimize all this stuff, we did very careful security proofs. You can see on the bottom of the slide, I have a link to a paper that we have on the Crypto ePrint archive. You can see all the security proofs for all of these VRFs that are specified in this draft. So everything we specify comes with the security proof that you can find there. In terms of the elliptic curve VRF, so the way we wrote it is we wrote the general VRF. Then we have cipher suites. So depending on what curve you want to use, what hash function you want to use, those are specified in the cipher suites. For this particular draft, we were very careful to deal with curves with cofactor greater than 1. So ED25519 curve has a cofactor greater than 1. We were careful to actually make sure that we did everything correctly with the cofactor. Our security proofs were actually also updated to include the cofactor in the security proofs. So that's the one major change that we did here. The other thing that we did is that we added a key validation function. So if you saw my presentation at SAG, what we were talking about, we were saying that if the public key was given to you by a trusted entity, then the VRF was secure. Okay, so if you trust the guy who gave you the VRF public key, then the VRF was secure. With this draft, we found a way to get around that requirement. So now you can validate that the public key that was given to you for the VRF is actually a good public key for a VRF. And why would you care about this, right? Because the adversary is the one who potentially is choosing the public key in some applications. So we want to have a way of verifying that the public key is secure. Okay, so I'm going to wrap up really quickly with the elliptic curve VRF and just to show you what it is. It's very, very high level. Okay, so our secret key is X. Our public key is G to the X. What do we do to hash an input? We take the input, we hash it to a point on the curve, that's H. Then we raise H to X, which is the secret key. Okay, so that's and then if you look at the corner of my screen, the screen over here, you can see that the actual hash output is just the hash of this gamma. So we take H to the power of X and compute the hash of that. That's the VRF output. Okay. Now I need to tell you what the VRF proof is. What the VRF proof is this value gamma. Sorry, I said alpha, but I meant gamma. This value gamma is part of the proof. And then there's these two values C and S. What are these things? They're a zero knowledge proof that gamma and the public key have the same discrete log, so they're raised to the same exponent. Okay, so we attach a zero knowledge proof that this is the case, and that proves to you that gamma is a valid hash of the input, right? Because gamma is h to the x. So you verify that whatever gamma is h raised to the power of x. You know h, you don't know x, but you use the zero knowledge proof to verify that. Okay, so this by the way, this is the pattern that you see in all the different implementations that we found in different places, and the details are in exactly how you specify the cofactor and so on, which we've done in this draft. Okay, so with that, I'll stop. Take questions.
Okay, thank you, Sharon. We have time for questions, comments. Please come to the mic, state your name.
Valery Smyslov, LSPAS. And do I get it right that this construction involves public key cryptography? So its performance is much worse than performance of classical PRF functions that are very often used for in places where performance is required, for example, for computing Mac. So this construction won't fit for this.
Yeah, absolutely. You would not want to replace PRFs with VRFs. Absolutely not. That's not what they're for. So there are very specific cases where you want to use PRFs. It is not just like now this is the better thing and we're not going to use PRFs anymore. Absolutely not. No, they're
Okay.
totally different types of primitives.
Thank you.
Yeah.
Brian Ford, EPFL. First, I just wanted to support this, general effort. I think, VRFs are indeed extremely useful, and actually another application case I'm familiar with has some very nice distributed password protection protocols and algorithms by Gregory Nevin and some others use VRFs that I know of. So that's, I think, yet another interesting application area you can add to the list. Just a question on the trusted versus untrusted public key and the verification function you added. Is that something that would also be solved by just using, say, a decaf encoding, or is it a separate? I haven't had a chance to read that part of the draft yet.
So I unfortunately don't know what a decaf encoding is, but we can talk about that after.
Okay,
I can tell
sure.
you that for the EC VRF, the elliptic curve VRF, the way that we do it, I think what we have to do is just check that the public key, if we raise it to the cofactor, is or is not a point in infinity. I have to check it. It's something really simple.
Okay.
It's not complicated. Like we take the string, we convert it to an elliptic curve point, we check that it's a valid elliptic curve point, we make sure that, that's all it is, and it turns out that that works.
Yeah.
So really,
Yeah,
the engineering task was not specifying the function, but proving that this function is sufficient for this to work.
Yeah. Well, anyway, nice work.
Brian, just a clarification, Brian, I don't think you could use decaf because you need to know the discrete log of the element that you generate, and I don't think decaf gives you that by design.
Okay, I understood decaf was mostly a mechanism to make sure that you don't get burned by the cofactor in doing, arithmetic, so that you canonicalize all points that have the same modular the cofactor. But I'm not an expert on decaf, so you could be exactly right. So.
This is Jeffrey Yeskin. Approximately how many bytes are the proof, and how fast are the operations?
Okay, so I don't know the numbers for the operations of how fast it is. For some reason, we didn't benchmark it before this meeting. But in terms of the proof, so that's an elliptic curve point gamma. That's one elliptic curve point. So if you do point compression, which is what's in the draft, that's 256 bits if you use ED25519. C is half of a SHA-256 output, so it's 128 bits. Getting this down to 128 bits, like we cut it in half, our security proofs showed that this was okay. So that was one big innovation from the security proofs. And then S is the output of a hash function again. So sorry, this is an exponent value, so it's again 256 bits. So it's 256 plus 128 plus 256.
Okay, any more questions or comments? So let me put a question to you as a group. What are your feelings about adopting this as a CFRG draft going forward? So we could do a hum. Are we allowed to do hums in the IRTF, Alexi? I believe we are. So I'm going to ask two questions. One, should we adopt this? Sorry, how do I do this? I say, we'd like to adopt this, and you hum. And then we should not adopt this, and then you hum. Okay, so let's start with, please hum if you think we should adopt this draft as a CFRG document. And for the opposite, if you think we should not adopt this as a CFRG document, please hum now. Or forever hold your hum. Okay, I think we've got a pretty clear consensus in the room that we should adopt it. We have to go to the list formally and ask on the list what people think, because not everybody can come to the meetings, and we'll do that in the next few days and get a sense there too. Okay. Okay. Thank you very much, Sharon. That's great. Thank you. Give it to Brian. Thank you. Just one second. Okay, next up we have Brian Ford from EPFL, who's going to be talking about collective Edwards curve digital signature algorithms. Thank you, Brian.
Okay. Yeah, so this is based on something we've been working on for quite a while now in various forms. The new development is basically we finally wrote the first draft of an actual attempt at an actual spec for a simple collective signing algorithm, and I'm going to mostly just go over. I won't get deep into the technical details for that. Read the draft if you haven't already. But I want to mainly kind of motivate it and talk about applications. Why this is interesting, because at this stage we're just trying to see if there's support for working on standardizing of this. Now, this is one of the many types of cryptographic algorithms that's motivated by splitting trust, avoiding single points of failures by building constructions that split trust more widely, so that no single compromised node or participant can compromise the whole system. And collective signing or aggregate signing or multi-signatures have a lot of different variations and several different names. This is the draft is one of a kind of constellations of possible ways to design collective or multi-signatures. But the basic idea is where you have multiple independent parties who want to collaborate to validate and sign some message or statement of some kind. And often this is a threshold group of some kind, T of n. It doesn't have to be. It can be. There can be more complex predicates like T1 of N1 in one group, and another threshold of another group also has to sign things like that too. But this is useful for many purposes. One is just for transparency, ensuring that many witnesses have seen something, and also to eliminate single points of failure. And a nice property of the Schnorr signatures of the type that RFC 8032 just standardized is they support this kind of multi-signatures very easily and efficiently. Again, without getting too much into the technical details, this is just kind of an illustration of the basic way this works. Any Schnorr signature is formally a challenge response sigma protocol. Basically operates in three stages. The signer creates a Schnorr commit, which is basically picks a random value, little v, computes g to the v to produce the public commit big V. Uses a hash function to turn that into a challenge. And then computes a response which is mathematically related to the private key, which is little k in this case. And the classic Schnorr signature is the challenge response. Now RFC 8032 uses the slightly different RS signature format, which is equivalent, but you know, kind of formally the difference doesn't really matter. It's just a representation thing. And so the fundamental modification to support multi-signatures is quite simple. All you do, you know, at least in the basic form, you have multiple signers now. You can have any number. Each signer has to create their own, have their own Schnorr commit. So each signer picks a, you know, v1, little v1, little v2, computes a corresponding public commit, big V1, big V2. Somebody, let's call it the leader, but it can be anyone. There's no one has to be trusted, especially trusted here. Someone basically combines all the commits together, computes a challenge. I should mention everybody needs to verify the challenge. There's a bug in the first draft that's being fixed that's important, but so everyone can compute or recompute and verify the challenge, and then everybody computes a response corresponding to their part of the commit, and then out comes basically, when you combine them together in the right way, out comes basically a single standard Schnorr signature, and this can be in either challenge response form or RS form. The draft is written with RS form to be consistent with RFC 8032, and so it kind of just works. And so basically you can then verify one of these collective signatures against the combined public key of all the signers all at once, with basically just the cost of a single signature verification. So this is, you know, nowhere near new. There's tons of background, theoretical background of, you know, this and different variants of this schemes. I won't go through these. Just going through some applications. So actually a year or two ago, I can't remember how long ago, I presented this this paper where we were experimenting with making this really scale and applying it as a transparency mechanism. Basically, the idea is you can take kind of any security critical authority service, maybe the DNSSEC root zone or a CA or any protocol you like. If you want to ensure that if it does something wrong, a lot of people will know, whatever, the complete collection of everything the authority signed, so the authority can't be coerced into secretly signing some backdoors or, some evil something or other without anybody knowing. Well, you attach this group of witnesses so that, the witnesses have to sign too, and make sure everything that gets signed gets logged, for better or worse, right? So without getting into the details again, basically we demonstrated that with the right protocols, you can make this extremely scalable, up to the thousands or tens of thousands of participants can work together to collectively sign messages in a matter of a few seconds. We don't, I don't think that any immediate application is going to really need that scalability, but it's nice to know we can get it when we want to. Verification cost in terms of CPU time goes down by orders of magnitude, depending on the kind of number of verifiers, as you would expect. And also, of course, you get significant signature size savings. Now, one caveat: the reason that that the collective version is not absolutely constant time, as you might expect based on the simple way I explained it, is that in a realistic collective signing scheme, you've got to have a way to tolerate participants that are failed or not online at the time you want to sign, and so you have to be able to adjust down, the group of signers to some set of signers that still satisfies a threshold. And so in the design proposed in the draft, there's basically we basically have a standard ED 25519 signature plus a bit mask. of the actual participants. And the bit mask is part of the signature in that it's fully checkable. You know, any attempt to change the bit mask will invalidate the signature. But so we basically need one bit per participant, and so so it's still linear, linear space, but way smaller. And although it's not really the emphasis of the draft, we can make this, and this is, this is optional. We can make this extremely scalable with tree-structured communication, but that's probably not necessary for most, small-scale applications. So I won't get into that. Other use cases. Cryptocurrency, the cryptocurrency community has been expressed quite a bit of interest in this for compressing the size of transactions by aggregating, a bunch of transaction signatures into smaller space. Again, I won't get into the details. Some of our own blockchain work has used collective signatures to build faster and more efficient BFT-based blockchains, basically using collective signing as a primitive as a scalability primitive within the inner loop of the BFT. And just extremely recently, actually, our latest work in this space, just coming out in the Usenix Security next month, extends this to use these collective signatures coming out of a blockchain to create basically a cryptographically verifiable and traversable blockchain that's kind of time travelable. If any two parties have two reference points anywhere on a time on the blockchain, they can prove to each other that any transaction they care about is indeed there, and with respect to the other reference point, either forward or backward in time. So for details, see the paper, but just kind of laying out some of the applications we think are interesting, and I'm sure there are others. I would welcome suggestions, kind of if you know of other applications that I missed, please let us know. Anyway, so again, I won't get into a lot of detail on the draft itself. This is only intended to be a starting point. It's definitely not perfect. We don't claim it's the ultimate or perfect formulation or representation or things. We tried to put some effort to align it well with RFC 8032. That's probably not perfect either. So it goes over the basic algorithms, and then a simple non-tree structure, kind of the simplest possible four-phase protocol for a leader and some co-signers to work together to sign things, and then briefly covers the more scalable tree-structured protocol for situations in which it's useful, and then message formats currently protobuf based, but we're not wedded to any particular format. Now there are plenty of questions. So if the group decides that this is a worthwhile direction to try to standardize, there are of course some issues, and this is to be discussed and decided. This is certainly an incomplete list, but some of the questions that we already know about. One is there's a trade-off between getting absolutely strict non-malleability of the signatures, which would certainly be desirable for various reasons. Not malleable signatures have burned, various people in the past. And so, yeah, we would like non-malleability. On the other hand, we can't get strict non-malleability as well as protecting against a certain type of internal DOS attack. So if somebody goes offline at the wrong time during the signing process, do you have to restart from scratch, or can you continue? If you want to be able to continue, you need some limited degree of malleability. So a trade-off potentially to be discussed. Another important topic is the way to defend against well-known related key attacks. So if I just use the simple algorithm I mentioned and take any collection of public keys, then I'm hosed. It's not secure because an adversary can compute a malicious public key related to other the honest node's public keys to cancel them out. That's not good. The standard way to do this is just to make sure that everybody who has a public key in one of these groups has proved knowledge of the corresponding private key. It's kind of standard cryptographic practice anyway. If you're using PGP keys to feed this thing, you're automatically covered, but it's an important caveat. Another alternative way of doing this that has some advantages and some disadvantages is to modify the actual signing and verification algorithm to hash the different public keys separately to eliminate that requirement at setup stage, but it has some important downsides too. So, and finally, the basic algorithm assumes that verifiers know the whole list of public keys that they're verifying the signature against. If we care about, if we expect that list to get very big and we care about the amount of state that the verifier has to know in its root of trust, then we can, we have ways of changing that, again, at some cost and complexity and stuff. So, and there are probably going to be more issues. So that's, so I wanted to leave it at that. So at the moment, the main priority here is to get feedback on, kind of, is this interesting and important and worth working to standardize, and kind of with the understanding that all of these issues, potential questions would be to be decided in that case.
Okay, thank you, Brian. Let's open the line for questions and comments. I see a race to the mic.
It's not a race. Yeah, Stephen Farrell. So, yeah, I think so this kind of stuff is interesting and useful. What's not clear to me is how would Cfrg know it's finished unless there's somebody actually saying, here's exactly what I need in an IETF spec or something like that?
Well, we are using this. I don't know, for a number of things I mentioned. But of course, I would love to hear other people, who would like to or are interested in using it, and I'm not sure how. So that's a good question.
Okay. I just I don't know the answer either.
Mm-hmm.
Phil Humbaker. Yeah, I'm very interested in this. I've not managed to get my head around the crypto yet. What I would like and what I could really use is, at the moment for encryption, I can split a Diffie-Hellman key into two. I can put a private key in a trusted platform module inside the phone that is unique to the device, never leaves it, and then have a second encryption going on at the application level, so that I don't need to trust what the manufacturer put into the device when it was made. Now, you said that this is a drop-in replacement for the ED 25519 signatures. Is it enough?
No, I didn't say it's a drop-in replacement. No.
Yeah, it's going
to. I said it's designed to be as closely aligned as possible in terms of formats and stuff. So it's not a big change from it, but it's a different thing, and it.
So I'm going to have a different verifier. I'm not just going to be able. I mean, with encryption, I can make it completely transparent, and you're not even aware that I've split
actually,
the key.
that's a subtlety. So that whether you need a different verifier is a subtlety that maybe should be added to the issued thing. It could be designed so that the ED 25519 verifier core, kind of the core 64-byte, ED 25519 signature is exactly compatible with the classic ED 25519. That would have some certain downsides. Because it would prevent us from messing with what goes into the hash and stuff. We wouldn't get to do. That would exclude the possibility of adding the hash of the bit mask in there for strict malleability and certain things like that. But that is an option that could be considered, and I'm very open to that.
Yeah, I mean, if you can do that, and I can do it as I will take any of the other compromises, because at the moment the only way that I can create a signature like that, basically, as soon as the public key, as soon as the secret that was used to create it is known, well, you blow up the whole system. So
I'd be very interested if you could.
Okay, yeah, that's I hadn't thought of that use case, but yeah, that's very worth exploring. Thanks.
This is Richard Barnes. Hey, Brian. It seems like we have a combination here in this draft of some cryptographic constructions and some protocol considerations. And a lot of these issues here are kind of at the intersection of those things. And it might have kind of some disjoint pools of expertise in terms of people we need to review this. I mean, do you think that there is
I thought that's what this room is for, isn't it? Like we have both here.
Most,
that's
yeah.
right.
Well, what I'm wondering though is how conjoined those two issues are, like whether it makes sense to kind of define the cryptographic construction that could be realized in various protocols and kind of develop the protocols separately.
By my understanding, the cryptographic part is basically already done and defined and formalized and proven in the collection of papers I cited on an earlier slide. We really haven't, added anything to that. There's, I mean, the only subtlety is, the bit mask and how that interacts with the kind of the standard cryptographic construction. There's, it would be worth, looking at that a little bit more closely than we have, but, I'm pretty sure that it doesn't fundamentally change anything on the crypto side. So this is mostly, intended to be about, kind of just defining a standard usable format in a concrete rather than abstract form, kind of that I can actually build a signer and verifier for it, and kind of a protocol, an actual functional protocol for producing these things. So that's the intent anyway.
Hi, Brian, Russ Housley. So I'm very interested in something that can be validated in the same way that Philip just talked about, but I thought, and maybe I misunderstood, that you said the verifier needed all of the public keys for the pool of potential signers.
So
that doesn't look like a public key on the verifier side, right?
Yes. So fundamentally, yeah. So fundamentally, that's not a requirement. So it depends on. Remember, there was the caveat about related key attacks that you have to be careful of, right? So if you the need for the list of public keys is partly related to the need for, if you're trusting this group of public keys, at some point you or someone you trust needs to verify that each listed public key also comes with a self-signature or a proof that the owner of that key really knows the private key corresponding to that. And so at that point, you or somebody you trust needs the whole list to check it. But you don't necessarily need that list at verification time.
Okay.
And
So
there's
let
ways
me
to
make sure
tweak
I got
so
it.
you can, okay.
Right?
Yeah.
So in other schemes, there's a dealer, right,
Yeah.
who gives, who
Like in the
avoids,
Shamir scheme.
yeah, or
Yeah.
the void split thing, and several
Yeah.
have dealers. And then, of course, you got to make sure the dealer forgets.
Yeah.
Right.
Mhm.
Here, you're saying there's a combiner, or there needs to be somebody that when each of them makes up their key pair, make sure that none of them are related or says pick again.
So this scheme does not require the public-private key pairs to be generated in any special way, unlike Shamir secret sharing. They don't
Right.
need to be generated for this. They can be, absolutely bog standard ED 25519 or ED 448 public-private key pairs that are used all the time for standard, RFC 8032 signatures. And once you have formed a list of these public keys and verified that, kind of a self-signature of any kind for each
Right.
one of them that can be generated in a totally standard way, then all you do for the actual verification of a collective signature is you basically just add together on the elliptic curve, just elliptic curve point addition, the public keys that actually participated in this particular collective signature according to the bit mask in the signature. Now,
Okay.
the bit mask is only there so that you can tolerate failures. So, if you want 5 of 10 nodes and 3 of the groups aren't currently available, somebody can still form a signature without them and just transparently declare, okay, 7 nodes were there, but those 3 were missing. So the verifier has to, take the full list of public keys and then subtract out the 3 that weren't there. And then after forming the correctly adjusted, aggregate public key, then it's a completely standard ED 25519 signature verification again. So in other words, you just first adjust the public key, the aggregate public key correctly, and then it's completely bog standard ED 25519 or ED 448.
So the verifier needs to know all the public keys to know what subtraction to do.
In the current formulation in the draft. So yes, that's one of the options to be discussed, though, that there are variations of that. So
Yeah.
that the second to the last bullet.
In my mind,
is-
trading off some trusted setup where the pool has to all be there and cooperate to do something.
Yeah. Mhm.
But then everything else from the signatures that are produced and the public key that needs to be certified
Mhm.
look just like ones that don't require a collaboration would be a big
Okay.
win.
So for that purpose, that combination of functionality, you probably really want Shamir signatures, which is very useful as well. And I'd be very open and supportive to standardizing that too, if people like Shamir better than this. So there are some trade-offs.
I guess I'm saying I can see protocol requirements for that right
Yep,
now.
I
Okay.
totally agree. Yeah. So, and I'm not sure where. So just to a couple of the relevant trade-offs. So kind of the Shamir sharing has a lot more complicated setup, but then you always get the same signature for any given set of signers. Shamir has, so if you want privacy of the signers, Shamir is better. If you want transparency and accountability, then this is better. Because with Shamir, you never know which particular threshold actually signed. And so if an evil threshold, a malicious colluding threshold signs something bad, they can all deny responsibility. I didn't sign that, and so there's kind of a somewhat subtle important trade-off there.
Okay, I think we have time just for one more question, if it's a quick one, and a quick reply, please, Brian. Thank you.
Thank you. Vasily Nikolaev, CryptoPro, a very short question about the performance. So the participants have to establish a secure connection with the leader, and how does it affect the performance of the whole signature, and does it still remain more faster than existing CMS multi-signature? CMS multi-signature.
The simple way to actually run the protocol, if we're scaling to like tens or even low hundreds of signers and not thousands, is you can just have the co-signers connect directly to the leader with whatever way you want. That doesn't even you probably want those connections to be secure for DOS attack resistance and stuff, but if they aren't secure, it's not going to produce bad signatures. It'll just, at worst, make the protocol fail to produce the signature you wanted. For scalability, kind of once you get into the hundreds, certainly thousands range, you start to not want all of the cosigners to have to connect to the leader directly, and then kind of the tree structures or other topologies become useful. But that's, I don't expect that's going to be the first use case anyway. So our experiments tried to explore that space. How far can you push it, and it looks like you can push it pretty far fairly efficiently. But I don't think you necessarily need to go to the full level of complexity in a lot of applications. Does that?
Thank you.
Okay, we're quite over time now, so thank you, Brian.
Just a very quick question to the room, like who is interested in reviewing this draft, and can I have a show of hands, please? 1, 2, 3. Okay. About 6 hands or something. Maybe I haven't seen somebody. Okay. All right. Thank you.
Okay, thank you.
So Kenny is going to present on behalf of Paul Hoffman,
Okay, yeah.
who is having conflicted session at the moment.
So I'm gonna channel Paul Hoffman to the best of my ability. That's quite a tall order, actually. So Paul has a draft, Hoffman C2PQ, which has been around for a while, and the motivation for his talk is to try and reanimate that draft and get people interested in it. So why should CFRG care? As he says on these slides, there's a lot of good discussion going on about what algorithms we should be using post-quantum, thinking about that, but there's not enough discussion going on around how do we deploy these algorithms, what is the likely timeline for the arrival of large-scale quantum computers, what the costs of deploying those algorithms will be when we need to switch over. And we know that changing algorithms, especially setting algorithms, is expensive, it's error-prone, actually it takes a lot of time as well. We have lots of experience of that in the IETF. So coming to his draft, it's not manifestly not about post-quantum algorithms themselves, it's about how we handle the timing issues around the transition to post-quantum algorithms. The draft is intended to address a number of different audiences, so execs, C-level people, I suppose, who want to understand the transition and what needs to happen when we get there. Security experts who want more information about quantum computers, their capabilities, how they will scale, what the cost will be, how fast they can break keys, and cryptographers and physicists who want something readable that they can point people to. So a sort of standing document that people can be directed to when they have questions about why should we be worried about quantum computers. Paul has admitted that the draft is quite incomplete, it needs work. There's a lot of sections that are missing material and references. It's really very much an early draft. There is not enough information there about the wide range of guesses that people have about when this might happen, whether it will happen, and indeed it might be too early to give useful guesses for that kind of thing, but at least we could document that fact and be honest about the uncertainty surrounding the advent of large-scale quantum computing. So Paul is proposing a particular way forward. He would like CFRG to adopt this as a work item. He would then bug people in the only way that, that's how Paul will operate, to fill in the holes and to suggest new parts. I think I, for one, would be interested to help him if I can to do that. He would like to get it discussed outside of CFRG at post-quantum cryptography events and general crypto meetings to get feedback on it, and aim to finish this document within a year or so, but recognize that it's only a snapshot of our understanding at that particular moment in time, so we would have to return to it some years later if we have better research or better information about how large-scale quantum computing is developing. And that's all of Paul's slides. So I'm very happy to take questions or comments, and I'll do my best to answer them.
Phil Baker. Yeah, one of the things that would help me would be to, at the moment, apart from Lamport signatures, there isn't a lot that I can go on. So from my point of view, looking at protocols, what I'm interested in is the size of the pieces of data and rough estimates of how much of the computing power, and whether it's going to be practical to do something that is post-quantum in public key, or whether we have to back out into doing Kerberos on a large scale, which is certainly possible, but might be challenging.
So in response to that, I would refer you to the first bullet point on this slide. It's not about the algorithms, it's about the transition and the timescale for the transition and how we should do that.
Yeah.
So they may not meet your requirements. That's Paul's intended scope. But I think that, speaking in a personal capacity, I think that's a fair comment. That's a big challenge for IETF as a whole.
Hi, David McGrew, Cisco. So I think it would be not a good idea if this draft discouraged people from using 256-bit keys. And so I understand, I believe I understand Paul's goal is to make people think about the costs of a transition and not rush into one and not make decisions too early. And I totally respect that and agree with that. But at the same time, you know, I have a number of customers, many customers who use AES 256 because they can as a configuration option. They say, oh, this is post-quantum, right? And they tick that box. And I don't think we should be discouraging people with that mindset.
Right. I think the current draft documents that exact fact. The major threat is to public key algorithms rather than symmetric key algorithms, Grover's algorithm, doubling the key length, etc. I think that's in there. But maybe it could be emphasized more strongly.
Hi, Stephen Farrell. So I have no real opinion about whether it should be in this draft or somewhere else, but I second what Phil was asking. I think kind of, you know, I think IETF people could do with input about the sizes and performance as known today of the possible options. I guess the sizes is probably more important in terms of, you know, future protocol changes, because you can maybe assume that some performance, you know, the sizes could be probably more precisely specified or ranges given now. I'm not sure.
I think we can certainly do that for hash-based signatures. We indeed have two drafts working their way through Cfrg at different stages where there are very concrete parameters. I think for things like key exchange and public key encryption, it's still very much a matter of development. It's up in the air. It's happening right now. I think the NIST competition, for which submissions are due in November this year, November 30th, is going to flush out a lot of concrete proposals with parameters. And then as a group, we might be in a position to get a sense of the kind of ballpark of the kinds of numbers we might be looking at without making concrete decisions about those numbers. So we should be able to get at least order of magnitude estimates.
Yeah, so I think, I don't think that information needs to be in an RFC necessarily, and nor does it need to be finished in a year. But if it was, some information was available somewhere, people would know what kind of things to start to think about.
Thank you.
Hi, I'm Darrell Piper. I guess to me this sort of falls in the realm of fear, uncertainty, and doubt. There's a lot of guessing here, and then there's a lot of hard science under this, and I'm not sure what the point is to bless a draft that kind of guesses and doesn't suggest any sort of real concrete way forward.
Okay, thank you. I'll let Paul respond to that one. Yes, the opportunity. Okay, so I guess the question for the chair is about adoption. Putting you in the hotspot, Alexei.
Yeah, can we have a show of hands of how many people are interested in working on this document in the Cfrg? If you're in favor of this, of working on this document and helping out, reviewing it, please show your hands. Okay. 1, 2, 7, 8 hands. That's not bad. If people think it's a waste of time and we shouldn't be doing it here, show of hands.
I know you're on the Jabber room, but 2 people in Jabber, Andreas and John, I forgot, I've already said they'd help work with on it too.
Okay. Okay, so I think there is some moderate support and nobody wants to admit that they hate the idea of it, so, or not. Okay.
Thank you.
Hi, I'm David McGrew. I'm going to be talking about some joint work that I did with Scott Fluer and Michael Curcio. And this is the latest iteration of the #SIGs draft. So what's new? Well, we did a security tweak, and that's the major difference between version 7 and version 6. And this tweak is motivated by an analysis that Scott did, which is posted up on ePrint. And I'll talk about that. That's the the most interesting part of my talk today. We also published, I shouldn't say we, Panos Kampanakis, one of my colleagues, and Scott Fluer published a comparison that's also on ePrint Archive, which compares this draft, this specification, with XMSS. And Scott also posted on GitHub a full-featured C implementation. And I won't be talking about that much later, but Scott did a good job of considering the different optimization strategies needed, especially for a signer, which is, it's a little non-trivial, so it's nice to see a complete implementation of something. So as far as security goes, Scott built on Jonathan Katz's previous analysis, right, which was called analysis of a proposed hash-based signature standard, and Scott's is further analysis. So again, this is in the random oracle model, and it assumes 128-bit security level. It demonstrates 128-bit security level for the SHA-256-based hash-based signature scheme. And the important difference is going to be described by the following, right? So SHA-256 is a Merkle-Damgard style hash function, right? And there are different security assumptions that you can make about a hash function in this model. So just as a refresher, the Merkle-Damgard hash breaks up the message, X is the vector at the top. It breaks it up into blocks, feeds these as inputs into the compression function denoted F here, and there's a chaining that goes on of the compression function. And then there's the padding that happens at the end, then you might truncate the output. So the different security assumptions you can make are these. You could assume the entire hash function is a random oracle. This is what Layton and Macaulay did in the 90s, and what Jonathan Katz's analysis of the more complex and more complete scheme recently did, right? You assume the entire hash function is a random oracle. Now, this is good in a lot of ways, but it also, we know that there are ways that hash functions are not random oracles. Hash functions are not random oracles because of things like length extensions attacks. Now, the previous draft was not vulnerable to a length extension attack, but we did analyze that. I should say Scott is the one who analyzed it in this other model, assuming that the compression function is a random oracle, right? So this assumption is much closer to actual cryptanalysis. If you look at cryptanalysis of reduced round SHA-256, this is much closer to that assumption. And in analyzing version 6 of the draft, arguably there was an attack that would shave off a few bits of security. So we tweaked the order of the elements, and it's not a big tweak, but it actually impacts the security analysis in this assumption, this model where we assume that the compression function is a random oracle. So a small change, and this is the motivation. So totally independent from what Scott and Panos and I did, Edward Eaton of Waterloo and Isara, that's a post-quantum security startup. Anyone from Isara here? No, guess not. So Edward analyzed the security of version 6 in the the quantum random oracle model, right? Which is something that is slightly different. In the comparison publication, the most interesting thing is probably the performance of the two different schemes. And essentially, the LMS scheme, the Layton-Macaulay scheme, is over 3 times faster. And these performance figures come from the published XMSS code being compared to the published implementation that Scott did of the LMS-based scheme. And we actually, he got something like, 4 to 5 times faster, nearly. For, the different operations vary and the different parameter sizes. In theory, you would expect something like a 3 times faster. So I think Scott spent more time optimizing his code and his implementation strategy. But at any rate, it's a very appealing performance number. So for next steps, I'd like to invite your input on draft 7. And we especially encourage you to look at the security analysis. And you please also do look at the comparison document if you're interested in understanding the differences either in security or performance. And if I could, I think a number of people have given us private feedback on the draft, so I encourage everybody to copy the Cfrg list, because we'd like to ask for this document, which is an official RG document, to go into a last call process so it can proceed forward. And then you never have to hear me talk about hash-based signatures again. You might have to hear Scott talk about it again. So, our point of view is that diversity of mechanisms is a good thing. And, we think XMSS is good work that deserves to be an RFC. We also think this work is interesting. We've heard feedback from some others who've implemented it. We know that there's at least one other implementation. And performance is attractive, and the security analysis has given us and some other people some confidence. And maybe lastly, this approach that we took in the LMS draft went back to a 1995 patent by Layton and Macaulay, which we felt was a good approach technology-wise. And we did, change some of the ordering of the elements and so forth, and we moved to a selection of functions to make it post-quantum secure. But our goal was to minimize the amount of innovation that we were doing so that implementers could claim the benefit of implementing an expired patent, or a technique where most of the description comes from an expired patent. So we think this is interesting, and we welcome your feedback. So thanks for your attention. I'll happy to take any questions.
Thanks, David. We have time for questions, comments from the floor.
This is Jeffrey Yaskin. As mentioned in a couple of the comments on the previous paper, it would be nice to have like sizes of signatures and public keys and private keys documented in the specification of the algorithms. So it's implicit in there, but it'd be nice to see it explicitly stated.
That's a great comment. Thank you.
I have a quick question. Could you go back to the slide with the performance figures? Can you explain what's happening in the second half of the table, where you seem to have like if I read it properly, a 1,000-fold improvement for public key generation? Or is that my misunderstanding?
I'm sorry, say again?
The second half of the table, PK gen for XMSS is something like 3,000 seconds, and you have 4.64? Did I misunderstand something?
So the last column is the ratio of the performance of the two schemes. So 3340 divided by 720 should be 4.64.
Oh, I see. Sorry, I couldn't read your table. Thank you.
Yeah, sorry about that.
No, my bad. It's totally my mistake. Thank you.
I was trying to go too fast.
Scott Fleur has come to the Micho mic remotely. Oh no, he's gone because I think you answered the question. I get a little Pac-Man here. You guys can see the Pac-Man too. Yeah. I think that's a great feature. Next.
Hi, Stephen Farrell. So I think in addition to size information, again, it might not have to be in an RFC anywhere, but it would also be useful to kind of know the different trade-offs and implementations that people have faced. So whether that would be just a presentation at Cfrg at some point, maybe that might be enough, but there seem to be a lot of them, at least from having read the XMSS stuff. There seems to be a lot of different possible optimizations you could choose to do. And I assume the same is true with LMS.
Yes. So the published code is pretty decent in terms of that. And that would, perhaps Scott could describe his implementation in the future. I think that's a very long topic, and if it's of interest to people, then absolutely, yeah, it would make sense to document some of that better.
Yeah, and I think it would be, well, I guess it would become of interest when people start to seriously look at using these things, I would think. And also some test vectors would be good as well.
Yeah, they're in the appendix.
Great.
Okay, thank you, David. So your request for last call is noted by the chairs. Thank you. Okay, we move on. We now have a presentation of Kangaroo 12. Unfortunately, the author Benoit Viguier couldn't be here, but we've got Quinn from NIST, who's very kindly agreed to present it. Do you want to take the clicker?
Thank you, Ken. I'm Quinn Dang at NIST. This is not my talk. They're not my slides. I was just asked to give this talk for the author. He's gonna come here. So the Cfrg team, they designed the Cfrg permutation like about 9 years ago, and we at NIST we standardized the SHA-3, including the shakes function. The shakes, they do have very high security margin, and the Cfrg team right now they designed a different hashing function which reduce like half number of rounds to make it faster, and I believe it's still very secure. And that function called the XOF, the ZOF variable output function shake 128. And in this function, not just the hash function, but the segmented hash function, the parallel version, which works very well today with the modern machines where you have multiple cores and multiple processors in machines. And the parallelism is really good. It goes with the size of the message, and they chose only one segmentation size, so which is good for a hash function which works everywhere. You don't have to choose different parameters and then end up with different functions. So this is a very nice function. And they got security proof in 2008, and they have further extension of the proof for their security in different modes, and the references are listed right there. And the nice thing about security analysis for sponge function with the permutation is that for Cfrg, you just increase or reduce around to do the trade-off between security and performance. And has been no tweaks at all since it was designed like almost 10 years ago. And the purpose doing that was that to make the analysis easier and to and so that people could understand the security better, and also you didn't have to do any tweaks which change everything. Which happens to a lot of different ciphers, when you do the tweaks and then your route function change. But this route function does not change except only the route constant. So this is really excellent design with the hope that to get a lot of independent analysis and to make people feel more comfortable and more confident about the security instead of different other designs, even including AES in the past. If we change something, that would become a completely different cipher. So the current attack, current security status right now is that for 5 rounds, people have found collisions on 5 rounds. And for the 6 rounds with the capacity C160, which is a lot smaller than the standard one, 256, people found collision on 6 rounds, and the complexity was around 2 to the power 50. And the best attack right now, as we know of, was done like a couple of years ago. from the paper from Eurocrypt, and it got to the time, even at the time 2 to the 128, even though it's the claim security level. However, the attack was really impressive, and they get through A rounds in predicting the next output of the function. So that was really good analysis paper. Excellent. And with the performance number for the short messages and long messages, for long messages you have excellent performance number, like around 1 point something, and even go down to 0.7 cycle per byte, per bit or per byte. So it's very impressive on modern machines. And again, the Shake28, the function can be used as a normal function. It's parallel function, but it is a normal hash function. You can replace any code and hash function with this function, and you will gain a lot of performance. So so as you all know, the Cfrg was a public design. You had the public design rationale. It has a lot of analysis and security proof in the original spec. And it was the result from the open international competition that we ran a few years back. And it's been very actively analyzed by the crypto community. And until now, it's been very actively analyzed by different cryptographers around the world. And it has been proven very secure. And the thing is, the speed up without wasting any crypto analysis, basically right now reducing around, and any analysis you had in the past still remain valid. That means because you did not change the permutation. It's just different constants for different rounds. That was it, and everything else was the same. And scalable too. If your machine has more cores, more processors, then the hash will be a lot faster, and it's not limited to anything. And with that, I would be happy to try to answer your questions.
Thank you very much. Please come to the mic if you have questions or comments, and state your name.
Kyle Rose. So I noticed that that Kangaroo 12 takes 3 inputs. It takes a message, a length, and a customization string, which sounds suspiciously like a label. Notice that we've had arguments in the past about having labels baked into.
I think the Kangaroo 12 takes the just a normal message, and as you use that hash function, then determine the length, and that would be it. That's a normal hash function.
Sorry, I'm looking at the draft, not at the slides. I don't know if there's a new draft plan.
If there is any customization string, I believe it is optional. I'm not an author, but I believe it is optional. Mm-hmm. So basically, you just take a message and you hash it out. But the shake is an XORF function, so you need to specify the length for your application you want to use.
No, it was the customization string that I was sort of pointing out. So
yeah. I think it is optional. I'm not the author, but I think it's optional. But thank you for that question. I think the author would appreciate that information.
Maybe I could ask a question, if I may.
Absolutely.
Does NIST have any plans to do anything in order to standardize this?
Right now, it's not a NIST function, but we don't know. I personally don't know about the future. But the thing is, in the past, good crypto coming out from the IETF, and we adopted them. For example, the HMAC construction, and also yeah, we did that, and
okay.
And we are in the in the consideration of adopting the new two curves, you know, the Cfrg produced over here. So we are in the consideration of doing that. So my personal expectation is that there's very good chance the curves will probably be endorsed or allowed by NERSC. But that's my personal expectation. The only thing I can say now is in the consideration of adopting those curves. So it depends on how things turn out.
Thank you.
And the thing is, because the Kangaroo 12, the function now, the security margin is still compatible to the security margin of SHA-2, or even a slightly better. So internal security is solid. Internal performance, it's 2 times faster than the current shake 128 for short messages, but for long messages, it's a lot faster. And one size fits all. Thank you for your attention.
Okay, so we're going to move to the last presentation of the day. Is Andrew Allen here? Ah, fantastic. Let's see if we can get the technology to work for us. So he needs to step on up, I think. I did try and contact him by email to see whether he was actually, but whether he could actually hear and participate. So Dan, if you can hear us, Dan Brown, it's your turn to do what you need to do in Micho and take the mic. I'll get your slides up.
Me? Can anybody hear me? Oh, send my. I can hear you.
Dan, if you can hear us.
Oh, can you hear me now?
Over there in Canada, where I assume you are. If you. Ah.
Can you hear me?
Did he come through there for a second?
And do you have my video?
Fantastic. Yes, we can hear you. Hi, Dan. Fantastic. We can hear you too. So we have your slides up.
Oh, I think I'm in the wrong mode,
perfectly.
so I'll just switch to my mode. There, okay. Can you still hear me?
Oh, I
Yep.
know. Maybe. Can you hear us now?
I can hear you fine. Okay. Yep.
Yes, we can hear you. Can you hear us?
Yes, I can hear you.
You can hear us okay? Okay, we have a little bit of a lag between the video and the audio, but I think we can handle that. So Dan, I have your slides up, ECC mod 8 to 91 plus 5. If you just
Okay,
say
great.
next slide, we'll try and keep things in sync at the
So
same
I just
time.
wanted to
So
first
take it
say
when you're
that
ready.
we're intending to comply with the IETF IPR policy. So next slide. And this work was, I basically wanted to find the simplest ECC parameters that were also remained secure and fast. So next slide. And so there's basically these features, and they have the benefits. So the main feature is that it only requires 6 symbols for the Galois field size. It's prime, and that's good because it avoids test keys backdoor and other security concerns. And it's not too big or not too small, and some well-known stuff. So let's go to the next slide. So this slide explains why the advantage of the plus 5 in the format in the prime here. It's because the format inversion step, which is often used in ECC, is very simple, and here's the code, and it's quite fast. So next slide. This slide is obviously too much to present all the information, but basically it's saying there's many other possible fields, and some of them are better in some aspects, but all of them are worse in at least some minor aspects. So none of them is better in all respects than this field. So next slide. Okay, so this slide addresses the question that the symbol count of 6 symbols, it seems a little bit arbitrary, but nevertheless, that heuristic still is somewhat reasonable. And so the 2 points to highlight here is when I use this heuristic for the field, I only came up with 2 secure and fast field sizes. That's in the bullet under just the term lucky. And then I only realized as I was preparing this talk that the one that I prefer of those 2 shares the same digits as the birth year of ECC. So I thought that was a happy coincidence. So next slide. So for this proposal, I'm proposing to use a very special curve because basically it matches the proposal to use a special field. It's very compact and it has many of the desirable features that we want, and it's listed here, and you can read it offline at your convenience. So next slide. So this is just one of those usual pictures that you see. I don't know if you guys can see the diagonal lines in the grid here. Perhaps not. They're a little bit faint. But it's not really necessary for the theme of the talk. So we'll just go to the next slide right away, okay? Uh-oh. I got disconnected. Can you still hear me? Okay, I'm back on. I see the slides. So what's this special curve has to great. This special curve
We can still hear you, yeah.
it has to forego many security features. But each of those features requires sacrificing some of the simplicity in the curve, and so there's always a fear that it may be vulnerable to an attack, or maybe otherwise. So let's go to the next slide. That sort of So we can be afraid of all these risks, or we can just go ahead and just try to dive in and try to use this special curve. And now next slide. So this slide is reminding us that Miller invented ECC in 1985, co-invented it with Koblitz, and he used very similar equations to the ones that I'm proposing to use. And he raised the issue, he asked whether it was prudent to use such special equations. And so indeed, yes, he was quite correct about that. Some of the special equations were attacked, the famous MOV attack. But in other cases, the cases that I'm proposing, there's been no published attacks since then. And in fact, such equations have been used in Bitcoin with great success, I suppose. Next slide. And in this slide, I just want to wish happy birthday to ECC. And that's the end of this talk. So there's another talk. If you want to take questions on this talk, we could do it that way. I'm happy to do that first, or the other way around.
Let's open the mic for questions from the floor on this specific proposal for this curve. Is there any comments or questions from the floor? Okay, I don't see any. So what I'm going to do, Dan, is switch to the other presentation, and then I'll give you a signal to go when I've got that up.
Great. Okay.
Okay, that's now displaying. So if you want to start,
so let's go
we're
to
ready
the next
for you.
slide.
Dan, we actually have a question on the last talk. So if you could just hold off 1 second, I think I can enable Scott. Go ahead, Scott.
Okay, I just had one very quick question.
The
What
cofactor
was the
is 72.
cofactor of the elliptic curve?
Dan, could you hear me?
Yeah, I heard the question.
Okay, thank you.
This is wonderful, isn't it? This technology. That's great. Yep, and I think you got the answer. So let's move on to the second presentation now, if you're
Okay,
ready. So Diffie-Hellman mod.
So let's go to the,
blah, blah.
the next
Go
slide,
ahead.
the actual first slide. Okay, so this is a slide reviewing Gordon's attack and the current countermeasures. And the main point is that the risk of a backdoor in Diffie-Hellman is actually quite real. Fortunately, we do have good countermeasures, but this proposal will do something a little bit better. So let's go to the next slide. Okay. So there's two main benefits of using this prime for Diffie-Hellman is one that it has a more compact description. So that's one perhaps informal but quantifiable way of measuring the possibility of there being a trapdoor. And the second security benefit is something quite unrelated. It has to do with Den-Bohr's proof relating the difficulty of the Diffie-Hellman problem compared to the discrete logarithm problem. And if you use this prime, then what happens is you basically nearly optimize that proof. So in other words, we have something that's nearly ideal in terms of Diffie-Hellman security, at least in the provability of that. So next slide. Oh, and this slide is just, these are highly speculative heuristics that are nice, but they shouldn't figure too much into a very serious analysis. So let's go to the next slide. I think that will be the end. Yep, so that's the end. Yeah, I'm done.
So you're done? Okay, thank you very much. So again, we'll open the floor for questions or comments on this, if there are any. Okay, thank you. Okay, so a question from me. You mentioned the relevant RFC 7919. Could you give us some feeling of why this is better than what we already have in RFC 7919? I guess Daniel is here, but too polite to ask that question.
Yes, so the RFC chooses a prime with a special compact form based on the idea going back to Gordon himself. And the only improvement here, well, the first improvement is that by being able to represent this prime in fewer symbols, that there's less room possibility for a trapdoor. Admittedly, that's an informal argument. The second improvement is that the Den-Bohr proof. So if you took that RFC 7919, which I haven't done yet, and you try to reconstruct the Den-Bohr proof, as far as I know, and the expected result would be that the proof would break down.
Okay, thank you. Anything else from the floor before we close the mic on this one? Okay, it seems not. Dan, thank you very much for your two presentations and for persevering with the technology. Appreciate your input.
The delay.
Yeah. So I think we're at the end of our formal agenda now. So if there are any other business that anybody would like to raise, bring to our attention, tell us about it, please come grab the mic. No, Rich. Please come grab the mic and tell us what's on your mind. Are there things that CFRG should be doing that we're not doing? Are there things that we are doing that we shouldn't be doing? I could go on. Okay, finishing on time. Okay, in that case, thank you to everyone for their inputs. Thanks everyone for the great presentations and for getting slides to us on time. It's been really helpful. And we'll see you in Singapore, we hope. Thanks a lot. Have a great time at the social this evening. Oh yeah.
There is an fetching data tracker. You can add document on agenda, which I did. I did
I
right
saw
after.
you did it. Yeah.